All right, good morning, everybody. Today is Wednesday, July 1st, so happy July. All right, so for tomorrow, we're just going to do Q&A for the exam. I'll pick up a couple of problems from the test that we can go over. If there's any specific ones that you notice from the practice exam that's on Moodle that you want me to go over, just send me an email today, or you can put it in the chat if you think about it or you have one ready right now that we can go over for the test tomorrow. Or if there's certain topics that you want me to cover, we can do that. But my guess is probably you might like some extra practice with synthesis problems, but that's just a guess. Homework 2 again is available, and then you have the labs that are available as well. You're welcome to turn those in at any point before the due date or by the due date. And then we have the exam tomorrow. So most people tend to like to go to the morning session and then do the exam either Thursday or Friday, but that's completely up to you to do that. Questions on any announcement stuff? All right, so we'll just go on to our recap here. So in chapter 18, we're looking at different aromatic compounds, and the most popular or most common aromatic compound is benzene. And a lot of these can have common names because apparently organic chemists of the past wanted to have short names for everything so that we'd have more things to memorize. So if you have a benzene with a CH3 group on there, that one is called toluene. If there's an OH, which we've seen already, that one is phenol. Anisole has an OCH3 group. Aniline is the NH2. We have benzoic acid, benzaldehyde. Acetophenone is the ketone version. It has the CH3 on the end. And then there is styrene. And you may have heard of styrene maybe, or polystyrene. So if there's a whole bunch of styrene units that get together, you get polystyrene, which is in the styrofoam cups. If you have multiple substituents on your benzene ring, you would use the parent name for one. So if it was benzoic acid and there was another group on here, this would be 2-chlorobenzoic acid. So you identify name substituents and then assign the locant or numbers, and you're going to arrange it alphabetically. So the rules are very similar. The tricky thing with benzene is trying to identify what the parent is going to be. Xylene is a specific name for two methyl groups on a benzene. So if it's 1,2-dimethyl, or they're two apart, it's orthoxylene. So ortho means that there's the 1,2 relationship. A meta relationship is 1,3. And then if it's para or across from each other, that one is 1,4. So if we're naming this substituent here, we have benzoic acid is the parent. And then we're going to number around the ring to give it the lowest numbering. If you have if you have two groups on the ring, that's when you can use the ortho, para, or meta. But if you have three things on the ring, then you have to go with the numbering. So this would be 3,4-dichlorobenzene. I'm sorry, dichlorobenzoic acid. All right, questions on naming those? Other things that we'll look at with chapter 18 is if a compound is aromatic or not. So in order for it to be aromatic, it has to have a fully conjugated ring with overlapping p orbitals, and it has to meet Huckel's rule. So it will have, and I always think of benzene when I think of something that's aromatic, it has to have an odd number of electron pairs. So in this benzene ring, there's 3 electron pairs. Or the number of total electrons is 4n plus 2. So in this situation, 4n plus 2 equals the number of total electrons, which is 6 here, and n equals 1. So if it doesn't fit that, where it's cyclic, fully conjugated, and n equals a whole number, then it's not going to be aromatic. Something that is anti-aromatic has to have a fully conjugated ring with overlapping p orbitals, an even number of electron pairs, or 4n total pi electrons, where n is a whole number. So the difference between aromatic is 4n plus 2, anti-aromatic is just 4n. If I look at this first example here, this is pyridine. It's cyclic and it's conjugated, meaning that there is an sp2 carbon or something that is has pi bonds that can contribute. So the nitrogen is going to contribute to that. That has an sp2 nitrogen. There's 3 electron pairs, which is odd. So this one is aromatic. This structure here with the nitrogen in the 5-membered ring, this is cyclic, but it's not conjugated because these are sp3. So they can't have overlapping p orbitals if there's sp3 carbons. So this is non-aromatic. And this next structure here, there's sp3s here. So this one is also non-aromatic. And in this cyclobutadiene, which has lots of angle strain, there are 2 electron pairs, which is even. It's cyclic and there's overlapping p orbitals, and the number of total pi electrons is 4n equals 4, because there's 2 4 there, where n equals 1. This one right here is anti-aromatic. So anti-aromatic is different than non-aromatic, which is different than aromatic compounds. So the aromatic compounds have the odd number of electron pairs, or the 4n plus 2 total electrons. The anti-aromatic has an even number of electron pairs, or has 4n total electrons. Okay, so how would we name this structure right here? Give the IUPAC for that one. So you got to figure out what the common name is there for the parent, and then figure out what the relationship is to that. All right, for this one, our parents, there's no ethylbenzene parent, but there's a common one here of aniline. So that will roll out A and B. And then we want the lowest overall numbering. This would be 1. If it's aniline, that's the number 1 spot. This is 2. So we'll have 2 ethyl aniline. You could also have named this one ortho ethyl aniline. All right, does anybody have questions on that one? All right, how about this one?
I have to go to the doctor. No.
All right, so this one, we have the parent for this one is going to be toluene. Anisole would be with a methoxy. So if I was drawing this one, this would be bromoanisole or metabromoanisole. So we ruled out bromo or methylbenzene. So toluene, this one should be D. So this one could also be para-bromotoluene. All right, questions there? All right, Brant, just so you know, you have your mute off in case you were going to ask a question. That's great. Otherwise, I just wanted to let you know in case you had noise that you didn't want us hearing.
Thank you.
No problem. All right, how would we characterize this one? Is this going to be aromatic, anti-aromatic, or not aromatic? All right, good. So everybody said that this is not aromatic, and that is because we have this sp3 carbon right there. So this is the correct answer there. Questions on that one? How about this one? We have cyclotetraoctene. All right, we have anti-aromatic for this one. That one is correct. We have our 4 pairs of electrons, which is even. It is cyclic and it's conjugated, so we have overlapping p orbitals, and then we have 4n equals 8 electrons, and where n equals 2. So that one is going to be anti-aromatic. And how about this one? All right, so this one is going to be aromatic. If we count up the electrons, the nitrogen lone pair here is contributing to the overlapping p orbitals. And so we have 3 electron pairs, or 4n plus 2 equals 6 total electrons, where n equals 1. So that one is going to be considered aromatic. Okay, so I'm going to switch gears. We have reactions to add to our reduction page, which is, for me, page 19. And this might be out of order from what we did in the lecture notes. But I'm going to start with a benzene that has 2 electron donating groups on it. We add sodium metal with methanol and ammonia. And this is the Birch reduction. So we start with benzene. And we're going to end up with cyclohexadiene. And this is the Birch reduction. So your electron donating groups can be R, which is going to be any carbon group where it's methyl ethyl isopropyl, something like that. You can have an OH there, an OR, NH2, or an NRH. So these are groups that have inductive abilities to donate electrons into the ring, or they have electron lone pairs that they can donate into the ring. So that is the Birch reduction with electron donating groups. We should also add the Birch reduction with electron withdrawing groups. But the other thing to notice here is that the double bonds are on the carbon with the electron donating group. And that's going to be the opposite for the electron withdrawing groups. So the same reagent. And now the double bonds, you're still getting cyclohexadiene, but the double bonds do not want to be where the electron withdrawing groups are. And the electron withdrawing groups are things that like aldehydes. So a carbon double bond oxygen, a ketone, a nitrile, a sulfoxide. If you have an N double bonded to something, carboxylic acid, or an ester. So the electron withdrawing groups do not want to try and stabilize those double bonds, so they want them away from them if possible. All right, questions there. And then we have reactions to add to the oxidation page. All right, that should be chapter 18 that we just added, not 14. This is 18. And this is with the Jones reagent. So before we use the Jones reagent, in order to oxidize a primary alcohol to a carboxylic acid, or you could use it to oxidize a secondary alcohol to the ketone. But if you have a benzene or a benzylic proton present, that is going to oxidize that to the benzoic acid or the carboxylic acid. So for this one, you need a benzylic hydrogen. So in order to do that reaction, you need a benzylic hydrogen. If you were doing this reaction with ethyl benzene and sodium dichromate with all the bells and whistles here, you would still get benzoic acid. So it's going to cut everything off. Or if you had if R was a 50 carbon long alkyl chain, you'll still get benzoic acid. So as long as there's a hydrogen here, that's going to oxidize here. And this tert butyl group does not get oxidized because there's no hydrogens on that carbon. All right, and then the next reaction is the same thing, but with KMNO4. So KMNO4 and the sodium dichromate have very similar properties. All right, and then I forgot about one to add to our functional group transformation page, because there's just the one. This one we've actually already seen in some form. And that is with NBS, which is N-bromosuccinimide. And that will place a bromine on the benzylic carbon. And this one also you need a benzylic hydrogen. And then that NBS is N-bromosuccinimide, in case you forgot. So previously, I think that might have been in chapter 11. So in last semester's stuff, we used NBS in order to brominate at the allylic position. So the carbon next to the double bond, this is doing the same thing, except it's on the benzene. So we can brominate right there. So if you have ethylbenzene or propylbenzene, this is a way to add an extra functional group that we can use as a functional group handle there. All right, questions on any of those reactions? All right, so what is the major product here? All right, so everybody chose C, and that would be correct. We have one benzylic hydrogen there. That's going to get oxidized all the way to the carboxylic acid, and all of that gets cleaved off. There's no oxidation at this position because there's no hydrogens there. Very good. All right, what about this same, or this, yeah, the same starting material with NBS and heat? So everybody chose A, and that is the correct answer. We're only going to brominate one time where there's a benzylic hydrogen. So C would not work because you've lost a carbon. And then B is benzyl or brominating the carbons and taking place of the carbon. So we don't want to do that either. All right, and how about this one? This is a Birch reduction. So this is the same thing as doing, actually this is not a Birch reduction. This one we didn't add to our sheet, but if you had hydrogen plus nickel at 100 atmospheres, which is high pressure, these reactions are usually done in a power bomb, which hisses and allows pressure out every once in a while, but it does sound mostly like it's going to explode any second. So I had to sit next to one of these in graduate school. But what this reagent does is it will reduce all of the double bonds in the benzene structure. Regular H2 platinum does not reduce double bonds. So what would this one do? Or what would our product be? All right, so D would be the correct answer here. And while that's fresh in our head, let's add that to the reaction page since I forgot to do that. I apologize. So that one will be on the reduction page, which was page 19. So to reduce benzene, you have 100 atmospheres with high temperatures. That will give you cyclohexane. So H2 platinum doesn't work regular on benzene. You have to use high pressure and then high heat. So some students on their total synthesis project use this method in order to reduce to their structure. So if you notice on the syllabus, your last you have 8 virtual labs, and then you're working on a total synthesis project where I assign you a larger molecule, and then you'll be putting together a synthesis for that large molecule. Okay, any questions on that reduction? All right, this one is the Birch reduction. All right, let's take a look at this one. So for the Birch reduction, you know that we're going to make cyclohexadiene, and we want to figure out where our electron, or if our groups are electron donating or withdrawing. And these have just carbon chains on them. There's no carbon double bonds. So these are both going to be electron donating, which for the Birch reduction, the carbons or the R groups that are electron donating want to hold on to that double bond. And the double bonds will be opposite each other. So A is out. The answer here is C. We're not going to reduce it all the way. So we're going to get this cyclohexadiene with the double bonds on each of the carbons with the R groups. This is what would happen B if you had electron withdrawing groups. All right, any questions on that one? All right, and what is this one? I feel like we did this one already, but maybe it was just similar. The first one we did was with KMNO4. All right, good. So we should get the benzoic acid oxidation there and not at the terp-butyl group. Good. All right, here we're looking at some IUPAC naming. So we have a couple of accepted things or things that you can prefer the common names. So there's 3 different IUPAC ways to name this one. So what IUPAC names can you come up with for this particular structure? Or what parent names are possible? Good, so phenol is one. So if we went with phenol as the parent name, that means the OH gets the 1. And then we have methyl at 2, And then bromo would be at 4. And we're going to list it alphabetically. So this one would be 4-bromo, 2-methyl, phenol. What other parent name could we have for this one? Toluene, very good. So that would be this one right here. So this would be 1. And then we want to number to give the lowest overall numbering. So this one I'm going to number clockwise. 2, 5. So 1 or the 2, 5 is going to be better than calling it 3, 6. So for alphabetical, it would be bromine first. So 5-bromo. And if you have an OH there, that one would be hydroxy. So 2-hydroxy toluene. And then the last one that you could name would just be plain benzene. And then we would go for the lowest numbering here, which would probably put the alcohol at 1, methyl at 2, and then bromine at 4. And then we list it alphabetically. 4-bromo, 1-hydroxy, 2-methyl benzene. Any questions on that one? All right, so let's look at A. Is this one going to be aromatic, non-aromatic, or anti-aromatic? So this is just for A. All right, so we've got a mixed bag here. A couple of things to remember if you're looking at whether or not something is aromatic. It needs to be cyclic, conjugated, which means it's going to have overlapping pi bonds or p orbitals. And then it needs to have the 4n plus 2 pi electrons. So if I go through my list here, this one is cyclic, the 3-membered ring. It's conjugated, so each of these are sp2 or has a p orbital, which that one does with the extra lone pair there. And if we look at the number of pi electrons here, there are 4 total. So if you could do the math on this, this is 4n plus 4. And n is not a whole number here. So that one is not going to be aromatic, but we can also check to see if it's anti-aromatic. This one is cyclic, conjugated, and it will have 4n equals pi. So if I do 4n equals pi, n equals 1. So this one is anti-aromatic. Questions on that one? All right, how about B? What about B? Okay, so this one is a little bit tricky. It is cyclic. And if you're looking at the conjugation here, the empty orbitals or orbitals with a negative pair of electrons in there are still considered p orbital. So this one still has a p orbital. So it is conjugated, and it has one pair of electrons or an odd number. So you can use odd. This one is aromatic. That one's kind of a tricky one. All right, what about C? All right, so this one is cyclic. We have the p orbitals here. Our electrons are 4, or we have 2 pair, which is even. This one is anti-aromatic. All right, questions there? And this last one, it's cyclic. We have all conjugated p orbitals. There's 1, 2, 3, 4, 5 electron pairs, which is odd. This one is aromatic. Okay, questions there? On the next set of problems, we're going to look at whether or not lone pairs are contributing to aromaticity. So we would see if the sulfur has 2 lone pairs there. And if you think about the sulfur without the lone pairs, would it still be aromatic? So in B, we have 2 pairs of electrons, which would be an even number, which would make it anti-aromatic. So that means that one of these lone pairs here needs to be involved in order for that to be aromatic. So this is a yes. So the lone pairs do participate there. In D, you have a similar situation. If you are just counting the pi electrons here from the pi bonds or the double bonds, we have 2 pair. So the sulfur is going to contribute that pair, just one of them, and that makes it conjugated. Nitrogen in the bottom corner also has a lone pair, but these lone pairs are not involved in the pi orbitals because N is sp2. So if N's participating in the double bond, then the lone pairs are not used. So this is yes here and no here. All right, so in the oxygen, E, the oxygen is part of the double bond. So it's going to be the same thing as the nitrogen. Since oxygen is part of the double bond, it is not using the lone pair there. And then what about G? Are those oxygens used contributing their lone pairs? Yes or no? All right, so if we look at G, there's the 2 pi bonds here. And without the oxygens, it couldn't be conjugated. So we do need 1 pair of those electrons in order to have the alternating p orbitals. So both of those contribute a lone pair. Questions there? Okay, so this is the structure of firefly luciferin, which enables fireflies to glow. And they actually use this compound in assays with enzymes to see if there's transcription that's working properly. So if your little wells in the cells glow, and to a certain degree, they know that things are working. And if they don't glow, it's not working. So this structure has 3 rings. Which of these rings are aromatic? And then which of them has lone pairs that help establish aromaticity? All right, so which of those rings are aromatic? Okay, so if we look at ring A, that one is just the benzene ring, and we know that benzene is aromatic, so A is aromatic. And B, let's say we have this pair of pi electrons right here. And this bond here is going to share the pi electrons from ring A, so that one can count towards that. So there's 2 pair of pi electrons. S has lone pairs that can contribute to the alternating. So then we have 3 pairs of pi electrons. This one is also aromatic. And if we look at ring C, there's the N, and then S has lone pairs that it can contribute, but we have 2 sp3 carbons here. So this one is not aromatic. And then if we look at letter B, the only one that is contributing lone pairs is the sulfur in ring B. Any questions on that one? All right, so here we're looking at products here. Draw the expected product when we oxidize each of these with chromic acid. So what would our products look like? All right, for this one, remember we're going to oxidize benzylic hydrogens. And we have 2 here. So we're actually going to get oxidation at both of those. So the answer here is B. That one going to be B. How about for C? What is your product going to look like for C? All right, so this one is a little bit similar, a little bit different than the last one. We're always looking for these reactions and looking for benzylic hydrogens. And that is on the carbon that is next to the benzene. So we have one here and one here. So those can get oxidized. Everything is going to get cut off. That's after that carbon. So that's going to get cut off. This is going to get cut off. The tert-butyl group has no benzylic hydrogen, so that one is going to stay put. So that would be, this one is not right. This one is not right. This is our correct answer here. So letter C is the right one there. So if we have no benzylic hydrogens, that group will get left alone. And if we do have benzylic hydrogens, everything on that's after that molecule will get cleaved off. All right, any questions there? All right, here we're going to work on a couple of shorter synthesis problems. This one is maybe 2 steps. So if we're looking at what is happening here, we're doing an elimination. In order to do an elimination, we need to have a leaving group. So you could have a leaving group here, or one at the benzylic position. And since this is chapter 18 and we just learned how to put a leaving group on the benzylic position, that is probably the easiest one to get to. So what we can do is add NBS. And you can add the BR there with NBS. You can also do this, I learned yesterday in the virtual lab, using BR2 and heat. But for this chapter, we can just focus on the NBS. And then the next thing that we're doing is doing an elimination. So we just need a base. And notice also the number of carbons has not changed. So the base here is DBU, or you can look at DBN or sodium hydride. All right, questions there? All right, what about this one? So our observations here, we are adding a CN. There's two reactions that we know how to add a CN, and that is using NaCN. So we would need benzene with a leaving group plus NaCN. Or benzene with a leaving group plus HCN. So this first one would do an SN2 reaction. This would be via SN1. All right, so if we look at this first one here, in both cases, we need to add a leaving group. So that would be using NBS. We add our bromine. And then here you could do NaCN. Or if you wanted, you could use HCN there. So both of those, NaCN or HCN would work. And you might wonder why the HCN will work going through the SN2 reaction, or I'm sorry, the SN1, and that is because that is a benzylic carbocation that would form, which is stabilized by resonance. All right, I'm almost back here. Let's see. All right, so the benzylic carbocation that would form, it looks like a primary, but this is benzylic. And that one is stable. So you could use HCN in order to do that reaction. Questions there? All right, here's another short one. What do you think about that synthesis? Ideas, thoughts? I'll give you a minute to work on that one. All right, observations that we might make here. I lost a carbon. So this C is gone. And now we have a carbonyl. And this is one of the mistakes that I noticed about the homework is that a lot of people lost carbons or they picked up carbons. This is from the week 1 homework during the synthesis process. So you want to keep track of your carbons. So I'm losing one here. And if I think about ways that I can make ketones, from benzene, I could have an alcohol here. That would be a way to do that. You could have an alkyne. Or you can do it this way. So if you had an alcohol, you could oxidize it. If you had an alkyne, you could do the HgSO4. And then for this particular one here, this one you could do ozonolysis. So which route do you think would be the most efficient route? All right, so let's try, we can actually go through all three of these syntheses and then see, then you can see what is going to be different about each of them. So let's look at A first. So in order to get to that A, this is route A. I need to make a group here. So this is going to be NBS. And if I'm looking forward a little bit, the only way that I can lose a carbon right now in my book of reactions is to do an ozonolysis. And so you can do a t-butoxide here. So I don't think we actually get to that one or a long way. So if I did ozonolysis, that would result in the ketone because we would cleave right there. And get that. So I guess by way of the other one, if you wanted to go through the alcohol, you could reduce it and then oxidize it again, but that doesn't really seem to make a whole lot of sense there. So I think the C is going to be your best bet here, and that's how you would do the synthesis with C. Any of the other syntheses would involve having to cleave a carbon somewhere, and the only reaction that we have right now that will cut that carbon off is going to be an ozonolysis. But if you didn't have, if you just had to synthesize this and you could go through the alkyne or the alcohol, then those would both be feasible methods. Questions there? All right, so which or what other products here when we're doing the Birch conditions? So this is the sodium metal with methanol and ammonia. My group here is an electron donating group. So that means that the double bond wants to be with that electron donating group. So my double bond will be here, and then the other one will be opposite that one. You could also have started the double bond going in the opposite direction. So you could have that one also, and then the one that we drew earlier. For E, if you have a carbon that's double bonded to something, that one is considered electron withdrawing. That one does not want the double bond. So the double bond will be away from that one. And then for F, we have two groups here. We have an electron withdrawing group and an electron donating group. So if we can make most of them or all of them happy, we can try to do that. The double bonds still have to be opposite each other. And we can't move our groups around. So the isopropyl group wants an electron or a pi bond, and that carboxylic acid does not. So I can draw it that way. So that one can make both of them happy. If you try to draw them the other way, then the carboxylic acid is unhappy. So that one is not the best way to go. Questions there? All right, so we're looking at a couple more synthesis problems. All right, so what observations are we making here? All right, so question, could we start with sodium dichromate or added ether? Yep, so we're actually, that dichromate comment was earlier. It must have disappeared in my window. So we are, let's see. Adding an ether. All right, actually, if I look back at that problem, was it this one? Yeah, actually, you could have started with sodium dichromate. So that would be another option to get to the alcohol. Except you'd have to, okay. So if we went back, sorry, I'm out of order here. If we did this reaction with dichromate, that will get us the benzoic acid. You could reduce that with lithium aluminum hydride to get the alcohol. We're still missing a carbon here, but that's okay. You could oxidize with PCC to the aldehyde. And then add a Grignard. We just want to add one carbon. Oops. So that will give you the alcohol. And then you could oxidize that again. So yes, you can use dichromate for that one. I think that might have been a couple of extra steps, but that synthesis would work as well. Again, you want to make sure that you keep track of your carbons there. So after I'd used dichromate, I lost these two carbons, and I had to find a way to bring that one back. All right, let's go back to the problem we started. Okay, so we're adding an ether. Ways that we know how to add an ether. You could do it with an OH plus a alkyl halide. Another way that we can add an ether is using the mercuric acetate, and that involves a double bond, but we don't have enough carbons there to make a double bond. So this is probably our only option here, is to go through this one. So in order to make the OH there, we need to have a leaving group. And I just lost the carbon. Okay, so leaving group there, and then we can do that with MBS. And you can do this via an SN1 or an SN2 reaction. So sodium hydroxide works okay, or you could use acid and water. Because that goes through the benzylic carbocation, that one is perfectly fine. And then what would we need to go from the alcohol aside from the CH2CH3Br? So what reagent is there? Number 2 is the CH2CH3Br. So our number 1 here should be sodium hydride. That will pull the hydrogen off of the alcohol, make that O-, and then that is ready to attack there. All right, questions there. So those of you that are here right now, what kind of things you want to look at for review for tomorrow? All right, so synthesis. I'll try to put, I'll find a couple of old synthesis problems and maybe give you guys a couple of options of synthesis that are already done so we can try to fix them or correct them. And then we'll look at synthesis problems on the practice exam. And yes, if you come up with things later, you can definitely email me later with suggestions. That was the last problem that I had here. So if you have questions, you can ask them now. I'll work on putting something together for your review for tomorrow. And also I need to write the exam. So if you have questions or comments or whatever, you can do that now, or you could just send me email later. Have a nice day.
Hi.
Hello.
I have questions for today, if that's
Sure.
okay.
Yep.
Not lots, but like a few. Anyway, I was wondering if we could go back to 9A momentarily for a second. I don't know why you formed like both of them.
It's technically they are the same thing.
Okay.
If you name them, it's still going to be, let's see, whatever this ends up being. But if you numbered it.
Okay, so
Around,
you're going to do that when it only has the one group on it?
Yes.
Okay.
Yep.
What else do I have?